recording. I do this recording in 3 parts, so then it's easier to handle for me also. Otherwise, the files get very, very large. The corresponding table in the from the book gives similar values for at least for the week. This one is some pKa is 1.92. I think I had it to in approximately the same region, but there is a problem actually with the equilibrium constants. If you consult different sources, then you will get slightly different values, at least as long as they haven't just been copying each other. But for the strong acids, for example, the hydrochloric acid, the acidity constant is 10 to the 7 in the book, and probably there are some reasons to believe it's more correct than my 10 to the 3. And the corresponding pKa value would be negative, a lot negative then. Hydrogen iodine acid should be the strongest simple acid, simple acid in the respect that it has a simple formula. It's not a composed perchloric acid, it's also very, very strong. But all of these acids, they are too strong in order to exist in aqueous solutions. But still, we speak about, for example, hydrochloric acid, aqueous solutions of hydrochloric acid. That is, what is this? And that is usually not a problem to speak about. If we would say, now my pen, we have no problem actually claiming HCl aqueous, but what is it? It's not molecules of HCl as hydrogen chloride molecules in aqueous solution, but it's very much more likely chloride ions and hydrogen ions. That hydrogen ions should better be represented as oxonium, or as the book says, it's hydronium ion, H3O+. The special name is oxonium ion, but there are other type of hydronium ions also. There is, for example, H5O2 plus, or H7O3 plus, or H9O4 plus. This is actually not at all uncommon. There are experimental evidences that indicates that this shouldn't be that uncommon. And for example, this H5O2 is experimentally detectable in some crystal structures. If you crystallize hydrochloric acid, one hydrochloric acid and 2 water molecules has a low freezing point in a way, but you can crystallize this, and then if you look at the crystal structure, you will discover such entities. And I'm not sure, I think you can find many more in other type of crystal structures, so low melting adducts between these acids and water. Well, just to summarize the product in water, the product of hydrogen ions and the hydroxide, they are equal to a certain value called the water constant, or if you take the logarithm of both sides, then you get this rule that pH and pOH is 14. Also, as we have seen, the Ka of an acid and the Kb of the conjugate base related to that acid is also Kw, or with a logarithmic version, you can claim that pKa of the acid and pKb of the conjugate base should be pKv. Don't mix pH with pK. They are extremely similar relations, but they're not. The terms are not equal to each other. So yeah, here was the actual picture I was looking for previously. An acid reacting with water, or a base reacting with water. Adding these two equilibria together will form something a longer one here, and when you skip the common, for example, HA and A minus, then the only thing left is water. This is mentioned in the end of the chapter in the book as a leveling effect of the solvent. And of course, I mean, an acid, HA, or a base, A minus, is an acid or a base in the context of being dissolved in some kind of solvent. If you dissolve this acid in another solvent, it's not necessarily a base, or it's not necessarily an acid, I mean, and the same applies to a base. So it's not at all unreasonable to think about choosing a suitable solvent for the reactions that you want to do. I don't know what you're working with, probably solid states, and so maybe you don't go into solutions a lot in your experimental work, but if you would, I mean, if it's reasonable to stay in water aqueous solution, then it's simple, because we have such a lot of water, and it's easy accessible, and it's hardly harmful, and so please stay in water. But if you need other type of environment, it may very well be worthwhile to try another solvent. For example, just changing to organic solvents like dimethyl sulfoxide, for example, DMSO, creates completely different environments. But then you also create extra problems for you in the experimental work, because you can't. You need to take care of the residues in slightly different ways. Sometimes we were looking at a titration curve previously, where we started with some acid, and here is a so-called free proton acid. We could speak about it as H3A. This is citric acid. This is an organic acid, and you can formally denote it as a free protonic acid. So if you start with that one and add in hydroxide ions, well, then pH increases, and then you reach an equilibrium point or equivalence point. It's nothing in this graph that indicates that it should be free protons. How come that we shouldn't interpret it as a single protonic acid and then increasing like that, and then we reach the equivalence point? Yeah, perhaps we should have expected a slightly different shape of the titration curve if it would have been a single protonic acid, but it's not easy to distinguish just from the curve here. From X-ray crystallography, for example, if we determine the structure of the citric acid, we can see that it's probably free protons that are accessible to be let loose. So they could be depicted as first one Ka1 maybe, and then this next one could also loosen hydrogen ions, 2 minus, and then we should call this Ka2. And the last, now let's see, minus. And it's the ultimate conjugate base, Ka3. So this is not unreasonable. And if these values, if they are close to each other, so of course this one should be the biggest, and the pKa of that one should be the smallest, approximately 3 here. Here is the pKa1 and pKa2 and pKa3. If the pKa values are quite close to each other, even though the later steps in the dissociation is weaker than the previous steps in the first steps, for example, then the titration curve would look very, very straight like that. We can speak about that it will have a high buffer capacity. Capacity is with C in English, yes. CT. It will have a high a property called buffer capacity that will eliminate pH shifts. At least the pH will increase when you add OH, yes, but not dramatically. So in this region, it will have a very, very high capacity. But when you have emptied the system, so to say, about hydrogen ions, then it will increase the pH very much. And here it's a very low buffer capacity. But if you need a buffer, and if you want to say keep the pH constant at say 5, then a mixture between these different, if it's H3A here, and at the first equivalence point you would have lost 1 hydrogen on average, and here 2 hydrogen on average, and here 3 hydrogen on average. So if you mix these dihydrogen citrate or hydrogen citrate, then you would have a quite stable environment. This is a way to make up a buffer solution. Suppose you want to keep the pH value steady in some experiment, and that could be of interest, because if you just if you just keep your experiment in water, then pH will shift a lot and you won't have any control of that. On the other hand, of course, these ions should also have no, they shouldn't interfere with your synthesis of such things. A graphical way, a graphical representation of a strong acid and water is given here. Suppose we have this strong acid, pen on, strong acid in water. And water we have also in a water aqueous solution. And then we know that if we state that water is the lowest pH is approximately around 0 and the highest pH is approximately around 14 for a water solution. Then the question is, a possible question is that, can you have hydrogen chloride in aqueous solution simultaneously as you have water? That is it possible to, in a beaker, for example, on lab, have an environment that has a pH of the lowest 0 simultaneously as it has a much lower, I don't know, this we can say it's -3 or something like that, -2, -3. So the question is, now let's see, I have problems with my pen. Can pH be less than -2 simultaneously as it is bigger than 0? No, of course not, because the pH should be a value in the beaker, in the solution in a beaker, because otherwise you would have concentration gradients, or then you wouldn't have a uniform mix in your system. So what happens? Well, the hydrogen chloride deprotonates, forming chloride ions. And where does the proton take away? Well, it attacks water, which forms oxonium ions. And this part of these two diagrams, they superimpose each other, and then they can exist simultaneously. I mean, it's reasonable to claim that a solution could be between 0 and -3 in chloride ions, as well as with oxonium ions. Perhaps this is not necessary for a simple thing like hydrochloric acid. Same reasoning applies to strong bases. Bases that are stronger than can only exist at pH values that would be bigger, larger than the largest pH value for existence area of water. But what will happen? Yeah, then the strong base will protonate, and water will deprotonate, and then they suddenly will have a common, those two parts will have a common existence area. I'm using this as a pre-check for the poor bear diagram that we will introduce tomorrow. So weak acids, then it's less interesting actually. What is a weak acid? For example, hydrofluoric acid. Can it coexist with water? Yes, it can actually, because according to this diagram, part of the green area here and part of the light blue area is coinciding. So it's no reason to assume that hydrofluoric acid should dissociate in fluoride ions, and it's no reason to assume that the hydrogen ion would protonate water. So the amount of it's unlikely that this fluoride ion and this oxonium ions should be produced. It's not completely unlikely, but probably since this is a weak acid, they can coexist with water, and they won't react very much, at least. Partly, yes, but not a lot. And the same applies to weak bases. Ammonia, for example, is an example of a weak base. Will it dissociate to a very large extent in ammonium? Will it steal hydrogen from water and form ammonium ions? Well, actually not. To a minor extent, yes. But ammonia and water can coexist. So most of the ammonia molecules will stay as ammonia molecules, maybe just coordinated by water. And most of the water molecules will stay as water molecules, be liquid, perhaps in association with the undissociated ammonia, yes. But a few of them will react and exchange hydrogens with the environment. And then if there are a few ammonia molecules that react, then of course there must be a few water molecules that also react, but not a lot. This is a weak base. This is another way of defining a weak base, that they can coexist with the solvent. So if you want to, now where was it? A weak acid. If you want to do these calculations of a weak acid, how acid will it be? We at least we call it an acid. So there are now let's see, what am I doing? There are different ways to calculate that, and maybe the traditional way and the most well-known way is the what I call an analytic approach. We state hydrogen fluoride reacting with water, and these are the products. Then we can claim that there is some concentration or some activity, yes, but I use the letter C as for concentration. The activity of water is unit because it's a dilute solution and it's nearly only water, and we don't have any product from the beginning. But at equilibrium, a few of them has been created, and as many a few of these HF molecules have been delivering hydrogen ions to water, and as many fluoride ions that has been created as then an equal amount of Athena quitted. We should just reconnect here. Lectures. Athena actually remembers. I don't know how it works. Now let's see. As many pen on. As many hydrogen ions as we have created fluoride ions, they need to be equal in a way. And if you create X number of fluoride ions, then the total concentration will be decreased. If X indicates the concentration of fluoride ions that are formed and oxonium ions, then the concentration that is left of hydrogen fluoride is C dot minus X. So then we just express this equilibrium constant, right-hand side divided by left-hand side. This is the formal definition. And you water, we don't need to include that. That is a unit. Or the formal, the symbolic concentrations or activities, x square here in the right hand side, and C2 minus X in the left hand. So multiply by that, and then you would have something, an expression like that. Rearranging a little bit, this gives a second order equation, polynomial equation, so it shouldn't be a problem. They can all be solved. And I don't know, there are different formulas if you interpret this coefficients by some symbolic values, then one can give a formula for the solution of the second order equation. This should work, at least in for real numbers. There could be problems if you solve a second order equation in complex number with complex coefficients, but that is hardly ever the case in chemistry. So then we try to do this. Here I define the Ka. This is I write this in a program system called Octave. It's similar to MATLAB. I just use it for doing calculations, and it will respond by storing the value Ka and C tot, and then we have an expression here, minus Ka half minus square root of Ka square divided by 4 plus Ka C tot. This comes from the expression down here. This is exactly the same as this expression, except that I printed it on my favorite calculator. So then I got the value of X. What does X mean? It was, among other things, the oxonium ion concentration, a negative concentration. Maybe one should avoid using negative concentrations. Perhaps not always, but you can define an acid solution as a hydroxide solution with a negative concentration of hydroxide ions. But that is perhaps a weird way of using the negative value. So avoid negative concentrations. This is unreasonable. Well, it was two solutions. We could also have a plus sign for the square root part. And in that case, the X became a positive value, and then one can then one can interpret this X as the hydrogen ion concentration, or perhaps the oxonium ion concentration, or even better, the activity. And then we can calculate the pH. It's the negative 10 logarithm. Log 10 is necessary to type in octave. I think it's the same in MATLAB. And you get the pH value 2.14. Is this reasonable? It was a hydrofluoric acid solution with a concentration of 0.1 moles per cubic decimeter. And it was a weak acid. Yeah, why not? 2.14 or 2.1 maybe. Now, this is a second order equation, and it should not be any problems actually solving this second order equation. But assume that you don't like this equation solutions and you want to do some simplifications, then you can actually do it. If now let's see, we had Ka C2 that if pen on Ka C2 minus x equals x2, that was what was written without any approximation. Suppose that we guess that this x is small compared to C2, then we can reformulate this equation equals x2. And this is then much simpler, even though the complete second order equation is not as complicated. But suppose you would get a third order equation or a fourth order equation or anything worse, then doing simplifications could be the difference between actually solving and not solving. Of course, with computers nowadays, you can solve a lot of equations that were more or less unthinkable for just 50 years ago. But when, or 100 years ago, when this theory behind acid-base theory and such things were created. But it's still useful to do approximations, I would say. So I'm using this Ka C tot minus x equals x2 in repeated approximation. First, I state here that for the computer to understand its has a value, I need to put in a value, an initial value. Then I solve for this unknown value as square root of Ka times C tot, but I don't skip the x actually in this version. I add it or subtract it here, but since it's 0, it's not visible in the first iteration run here. Then I get the value of x value, the concentration, and I can calculate the pH of P 2.12. This is nearly like 2.14 as we had from the sort of exact solution. But with this value of x, we can repeat. With a computer, it's easy to repeat things. They don't hesitate to calculate. They don't do it fast, and they don't do it accurate, but they don't hesitate at least. And we get another value and another pH value. Let's repeat the calculation, and we get another pH value and another pH value. So after a while, it doesn't change. And we can say that this iterated calculation has been converging. This is perhaps I like this convergent series, from crystallography maybe, but this is a way to simplify a calculation when if you don't want to use a long, complicated expression. Here it's not obvious, but if we didn't have any one can, if you want to take into account the autoprotolysis of water and include the solvent effect, then this second order equation will transform into a third order equation, and then immediately it's much less feasible for at least manual solution. You can of course solve it with the Octave or MATLAB, or if you have a symbolic handling computer algebra system, you can in principle solve most usually occurring equations without any problems, even higher orders. At least as long as they are polynomial functions and such things, then it's no problem. Is it any simpler way? Well, let us look at hydrogen fluoride again with something I call simple diagrams. We just denote them by, let's see, pen on. It's a simple diagram. It's just a one-dimensional, the acid form and the base form of the hydrogen fluoride. This is the pKa value. So what I mean is, above the pKa value, the base form dominates, or close to pKa, both the acid form and the base form exist, no problem. But at high pH values, far above pKa, then the base form dominates. And when does it start to dominate? This is difficult to claim anything from this simple diagram. And below pKa value, the acid form dominates. And how far do you need to get into the acid area here in order to be able to claim that it's only acid form and no base form? This is difficult to claim from this diagram. But we can still use it for doing calculations. Or at least if we do understand the meaning of pKa value and this distribution, this simplest possible distribution diagram, then we need to check a few things. Suppose that we had a total concentration of 0.1 moles per cubic decimeter. That was the premise for the calculations previously, when we got pH of 2.14 in the acid solution. How acid could the solution be? What is the lowest possible pH value of a solution with this concentration? Well, the worst acid, so to say, that could be in water is H3O+, which would give rise to a pH, if we would have had 0.1 moles of oxonium ions, then the pH would be 1. So that marks the end point of the acid region. This region, more acidus than pH 1, is not accessible with a solution of this total concentration? Well, let us continue a little bit. On the opposite of an acid is a base, and the worst base that could be the strongest base that could be present in water solution is hydroxide ions, and if that would be present in, there are a lot of ifs here, sounds like a computer program. If that would be present in 0.1 moles per cubic decimeter, then the similar to the oxonium ions, the pOH would be 1, or the pH, the maximum pH would be 13. So that indicates a limit for how basic, how alkaline a aqueous solution can be with the concentration of 0.1 moles per cubic decimeter. Why do we need those? Well, actually, then I claim that the pH of a solution of the acid form is the center of the existence area. So it's the average value of the pH minimum and the pKa value, and then divided by 2 as calculated the average. That's 2.15. This is, well, we got 2.14 previously, and I would like to claim that these are very, very similar. It's difficult to define pH in the second decimal, and especially, well, you have 5 students here. If you would grab 5 pH meters newly bought and fresh in every respect, and measure one and the very same solution, I'm sure that you wouldn't get 5 identical values, but they would be slightly different, say up to 10 or 2/10 of a pH value difference. They need to be carefully calibrated, the pH meters, if they should report a significant true value in the second decimal. So in that respect, 2.15 and 2.14 is similar. But on the other hand, this 2.15 was the result of a much, much simpler calculation. In addition, we got as a bonus the pH of a solution of fluoride ion. Yeah, it's also the center of the existence area. What is the average value of 3.3 and 13? Well, it's 8.15. And this one can, of course, also obtain with the analytical calculations. And I wouldn't say that one way is better than the other. Yeah, maybe analytical calculations, they can be wrong if you don't see the whole picture. But a risk with analytical calculations is that you don't take every possible aspect into account when you do solve an equilibrium problem. If you do that, they won't be wrong, and they won't fail you. But it's good to have an overview. The question regarding whether it is when this domination over the acid form, when it ceases, well, acid, and then suddenly the base form, this can't be a good representation of reality, and it isn't. Then one can draw something called a fraction curve. The fraction of the red curve here is the acid form, and the blue one is the base form. For an acid, with a pKa of 3.3. That is similar to hydrofluoric acid. And here you see that at lower than pKa value, the acid form, for example, 80 here at I don't know, 2.5 or something, 80% of the molecules are existing in acid form, and say that up here around 2 or even below 2, then most of the acid form, they actually most of the molecules are existing in the acid form, but there are a few left of the base form anyway. If you ask the question, how much of the acid is still remaining at pH 10, then this diagram doesn't give you any answer. Approximately 0 is the answer that one is the conclusion that one can draw, nothing else. If you want to know that, then what to do? Well, after a while, you realize that take a logarithm of this axis, and you would get something called a logarithmic diagram. Now let's see if I can remove this bar.
Lasse, you're muted.
I was still kind of curious.
Sorry, I'm muted. Sorry. Thanks. Thanks. This axis is the fraction times the total concentration, and then if you type the logarithm, then it would be negative values everywhere here. But if we say that it's it should, let's say that we give the negative logarithm here, that is the PC, then they will be positive values. And the difficult thing with this one is that the positive y-axis is pointing downwards, indicating low concentrations down here and high concentrations up here. Similar to pH, but pH is so common for most people that we don't, we have incorporated an opinion, what is pH 14 or what is pH 4? Well, pH 4 is a higher concentration than pH of hydrogen ions than pH 14, which is a lower concentration. It's the same P here. So this is the acid form, and the base form is the blue one, similar to the diagram. C-tot was 0.1, so P of C-tot must be 1. So this means that the total, the line here can never go above the concentration, the logarithmic representation of hydrogen HA can't be more than 1, similar to the logarithmic representation of the base must also never be bigger than 1, assuming this. So we speak about the PC dot line. So, now let's see. This diagram is of course a bit strange, but you can have computer programs that produce them, and I will introduce some computer programs. One called Medusa that easily draw these. And they are actually of interest to use, because if we look at what is present in the solution, the initial species in the solution, they are fluoride ions and water. So let's make the economy type of view on the hydrogen ions. Fluoride ions can't donate any hydrogens, but water can, and then it forms hydroxide ions. Both of these species can, on the other hand, attract extra hydrogen ions, and fluoride ions would form HF and water would form H3O+. So where do these hydrogen ions come from? They come from some species that have lost hydrogens. So the idea is that the sum of everyone that has got an extra hydrogen is equal to the amount of those that lost the hydrogen. This is what we call a proton condition, or possibly a protolysis condition. Protolysis occurs in the sense that hydrogen ions are moving around between the possible species, and some of the species will be protonated, but as many of them that are protonated, as many would be as many of the some others would be deprotonated, because there is a limited supply of protons in a solution, since they occurs in the same beaker, so to say. How to interpret this proton condition? Yeah, if we say that HF plus, it is actually not, this diagram shows the logarithm of everything. If you have an equality of a linear term, and then it's also should also be an equality of a logarithmic term. Here is a problem actually occurring, that the logarithm of a sum is difficult to express in terms of the individual. So say the logarithm of a plus b, this is very difficult to express. On the other hand, logarithm of a times b, that is easy. That one can expand like that. But unfortunately, this is not the case. We have this more or less impossible way to, maybe one can do a series expansion or something like that, but that has never been used in acid-base theory. At least I don't think so. But we can see they need to on the right hand side we have a single variable. So then we can follow this pen. Then we can follow this hydroxide ion line. So here seems to be some equivalence. Is this the expression? No. Here the logarithm of OH should be equivalent to logarithm of A minus. This is not at all present here. So then we skip this one. We continue along the OH line. Here, logarithm of OH should be equal to logarithm of HA. That is, in this case, HF. Is this equal? Logarithm of OH equals logarithm of HF? Yeah. Well, 2 out of 3 is not bad. See what to do with this one. So at this point, where is H3O plus? It's 2 units below. And on a logarithmic scale, on a 10 logarithmic scale, that means 100 times smaller. So then we can approximate that to be negligible. And then we actually found this proton condition representing the exchange of protons in a fluoride ion solution would give a pH equal to, well, we can record it, or we can calculate the average between pKa and what is this? This is, if this was 1 and this is 14, so this must be 13. So pKa and 13, here it's 8.15. Similar to what we arrived at previously with the simple diagram. The simple diagram is actually, in this respect, it's this cutout from the logarithmic full diagram, where these two are the limits. There can't be more hydroxide ions in a solution than we have object molecules that would form hydroxides, and similarly there can't be more oxonium ions than we have acid molecules. Here is the pKa value, and this is the 2.15 point. The average value between the minimum and the pKa, and 8.15, the average value between pKa and pH max. I'm not sure that you appreciate these diagrams. Actually, I know that people hate them, but you get used to them. I think we should have a leg stretch and maybe some filling up of coffee in 5 minutes. Is that reasonable?
Sure.
Yeah. Okay. 5 minutes.